Okay guys, in this video lesson, we're going to dive a little bit deeper into this idea of forces and how we can map them out to understand how they work together or oppose each other. So the first thing we want to do is talk about a force vector, okay, and what that kind of is for us. Remember, if you recall, vectors are used to represent forces and direction, okay? So we're going to have both the magnitude here and the direction that we're dealing with as we take a look at this idea, all right? Now, if you remember, they're arrow systems. So when we look at forces, what we see going on here is arrows are represented of both those magnitudes and those directions. The longer the arrow, the larger the force. The shorter the arrow, the smaller the force. Okay, so that's what we're kind of looking at and moving forward. So if we were looking over here at these three arrows, we would say of the arrows, the green one here in the middle, that one is our largest force, and it's pointing to the left. The blue would be our smallest, and the red one would be someplace in between. All right. The other idea that we have is that we can actually take a look at forces that are opposing each other, like we see for the yellow and the purple arrows here. So the yellow and purple arrows have the same magnitude in force, but they're opposite direction. So what actually happens in this scenario, if we were watching this as a physics scenario, they'd be canceling each other out in terms of that. Also, because we're dealing with forces, everything is in quantities of newtons. Now, with force vectors, we can put them together to draw something called a free body diagram, okay? And what a free body diagram does for us, it maps out all the forces acting on an object at one time. And then from those different forces, we then can start to get a better visual on what is going on with our free body diagrams and what's going on with that object moving through space. Okay, free body diagrams always show us the direction of the forces and how much force is acting along this. All right, so if we come over here to our first free body diagram, most of the time to do a free body diagram, you just start by drawing a box of some sort, like we see here in this one, and then we use the arrow systems, like you see here, 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 and here, to represent the forces acting on it. Now, in this case, this is probably a box that is just sitting on a table someplace, and it's being pushed along. You have the force of gravity pulling down on it. This will always be, always be around our forces. Okay, so be ready for that. And then we also have the normal force. We know it's sitting on a desk or something because the normal force is present. Right? We have force being applied to the right, and we have friction in the opposite direction of that. Okay, so in this scenario, what we have is we have the same length arrow here as we do here. Same length arrow here as we do here. So this object is probably not accelerating. This object is probably either moving at a constant speed, like cruise control in your car, or it's not moving at all. It's just sitting still. Okay? But either of those are options because we have the same length arrows for both the friction and the applied force and the normal force and the gravitational force. All right? What we're going to do now is actually draw some free body diagrams ourselves. And we're going to take a look at what they are and kind of how they work. All right? So the first thing we have is a book that is resting on a table. And with the book resting on a table, what we want to do is to draw a free body diagram is to start with just a box. So we have a little box here. And now we're going to draw our forces off of that box. Okay? And because it's on a table, we know that we have gravitational force pulling us down. And we know that we have the normal force moving us up. Okay, so this right here would be force normal. This would be force of gravity right here. Okay, now we also know it's resting on that table. So because it's resting on the table, there are no other forces acting on this box. All right, so that would be one example of a free body diagram that we have. All right, and I drew it pretty much the same as what it shows on the screen. Next one down here, we have a swing hanging on its chains. All right, so now we have a swing and it's hanging on its chain. So I'm envisioning, a swing coming down. There's a little thing right here, a little seat for that. So I have two different chains I need to work with in terms of this. And I'm looking at some tension now because the chains are going to provide tension force to that swing when someone sits on it. All right. So again, I'm still just going to use a box to diagram this thing out. So I'm going to have a box right here. And I'm going to put in my forces. So in this case, I have two strings holding it up. Those are going to be my force of tension, okay? And I already see that one, okay? And then we're going to have the gravitational force, of course, pulling it downwards, between those things. So that's going to be my force of gravity, okay? And if we take a look at how I drew it versus what the free body diagram is on here, we have our two things of tension, and then we have a gravitational one. Now, one thing you want to keep in mind is, and I didn't do a great job of this, but my force for gravity should be 2 times longer than these are, okay? The reason being is if the swing is not accelerating up or down, the tension that combined from these two things here should equal the force of gravity pulling down on it, all right? So this is probably a little bit better drawing here. Notice how these two added up probably would equal that. So you'd have your tension coming up and then your tension again, so they would cancel each other out in terms of their overall forces here. All right, so that's our second example. Go ahead and pause the video here and try to do the other 4 that are on the screen yourself so you get an idea of how to do these, and then unpause the video and you can see how they're done the right way. Okay? So assuming you paused the video, or you didn't, who knows, here's what we get for the rest of them. So we now have an egg in free fall, okay? So with an egg in free fall, the only thing we have is force of gravity. It's in free fall, all right? And then we have a car accelerating to the right, all right? So in that case, let's take a look at everything that we got here. So we have gravity, which never goes away, the normal force, which is counteracting it, okay? And we have friction, which is going to pull against that car, and the applied force. Now the trick here is noticing that the friction force in that direction is less than the applied force. So our force of friction here is less than that applied force here. That's how we know it's accelerating, okay? If they are the same length, then they would not be accelerating. So we can see that from that force there. And then our last one, we have a car, no, sorry, not our last one, second to last one. We have a car moving at constant velocity. So now, not like this one here, now the friction force and the applied force are equal to each other. Thus, we get in a scenario where there's no acceleration. But we still have normal force, and we still have gravitational force on this one also, okay? And then our last one, if we take a look at that one, we have a bike rolling to a stop, okay? So in this case, with a bike rolling to a stop, there is no applied force because it's just rolling. The normal and the gravitational force still should be the same here, but it's rolling to a stop. So there has to be a force that's opposing the motion. And friction force opposes motion as we take a look at that, okay? So that's kind of the idea of free body diagrams. We'll draw a lot of these as we move forward. They just kind of help give us a visual of what's going on and kind of how things work as we are working through these different scenarios of forces acting on objects. Now, once we get free body diagrams done, we can start talking a little bit more about combining forces and what that means to us, all right? So it's very common to have multiple forces acting on an object, all right? When that happens, we're going to add them together, okay? Or we're going to sum them. We call that sum the resultant force. So we have our net force or our resultant force acting on our objects, okay? For example, if I had an object that was had a force applied to it of, let's say, 200 newtons in this direction, and I had a friction force that's pulling back on it, let's say that is, 100 newtons, okay? What would my force net be here, okay? So in that case, well, we would take the 200 newtons minus the 100 newtons, and my net, or my overall force I would get then, would be 100 newtons of force in this. So I'm going to net force acting on things because friction opposes the motion, or it was opposite of that, all right? So that's one way we can look at this, and it's important to us because we often have friction to deal with in terms of canceling out part of our applied force, okay? Now, if we get a net force acting on something, okay, we no longer can apply the first law. So the first law of motion, remember, talked about no net force. Well, we don't have that scenario here. If we have a net force, that means that we cannot use the first law anymore to talk about. So we need something else. All right. And what we're getting here is a change in motion. Okay. So let's go back to what is a change in motion called? Okay. Remember, when we get a change in motion or a change in velocity, that's an acceleration. So what happens is when we have a net force, that means we have an acceleration. If we have an acceleration, we cannot apply the first law of motion, so there has to be something else that determines that. All right? And what determines that is Newton's second law. All right? We're going to stop the video here, and we're going to go back in our next video. We'll dive into Newton's second law. Thank you.